Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit number 10, Lesson number 3 on the area of polygons. Alright, so Unit 10 is all about measurement and modeling. And in the last two lessons, we looked essentially at calculating distances, right? In terms of straight line figures, we were talking about perimeter. And in terms of circular figures, we were talking about circumference. But really, at the end of the day, they were still just lengths. Area is completely different, all right? And let's jump right into it, because this is important. Area is a measurement of the amount of space enclosed by a two-dimensional figure, the amount of space that's inside of a two-dimensional figure. It's typically done by counting the number of squares of a given side that fit inside of a figure. So we talk about the area being 3 square feet, or 22 square meters, or 15 square centimeters, right? And what we're literally doing is counting the number of squares of a certain size that I could put inside of a figure. Maybe I have to cut some of them up and rearrange them, but ultimately how many squares fit inside. So let's start with an exceptionally easy problem. Exercise number 1. If a rectangle has a length of 8 centimeters and a width of 5 centimeters, then what is the area of the rectangle in square centimeters? Pause the video now and do this problem very quickly. Well, hopefully you said 40 square centimeters, right? The area in general of a rectangle is length times width, and in this case that's going to be 8 times 5, or 40. Now, the reason that I drew the picture this way is to really emphasize that this isn't so much a formula as just what it means to multiply, right? If I've got a rectangle that's got 1, 2, 3, 4, 5, 6, 7, 8 centimeters along this side, not square centimeters, 8, literally there's this a ruler with 8 centimeters, and 5 centimeters, then there are 40 of these square centimeters, right? A square that is 1 centimeter by 1 centimeter, well, there are 40 of these that fit inside of here. And you could actually count them. You could be like 1, 2, 3, 4, 5, 6, etc. I don't want you to, but you could. And it's important to understand that, right? That's why I'm a little bit, I don't love this terminology, and I really dislike it, and I do it myself, right? But I really dislike it when people say that the area is 4 centimeters squared, right? Or 40 centimeters squared. It's 40 square centimeters. A square centimeter is an object. It's this thing. And there are 40 of these that fit inside of here. All right? Let's do a little review of some common area formulas that you've seen before. All right? You've got the area formula for a parallelogram and the area formula for a triangle. The area formula for a parallelogram, very simple, right? If we've got the base length and we've got the height, then the area is simply base times height. All right? Likewise, for a triangle, right? If we've got the base and the height, and remember the height has to be the perpendicular distance from the base up to the highest vertex, then the area is 1/2 of base times height. And you should have looked at both of these formulas extensively in 8th grade math, right? You should have seen where they come from, how you can basically slice a parallelogram in half and get a triangle, how you can rearrange a parallelogram so that it looks like a rectangle, and that's why the formulas are the same, base times height. We're going to take it as a given that you've explored these, that you understand these, and now we're just going to use them. So let's get into this, okay? Kind of like our lesson on perimeter, right? The first one of this unit. The point is that we're now going to be using more sophisticated rules or tools of geometry in order to use these very simple formulas. Now let's take a look at exercise number 2. A patio is to be made in the shape of an isosceles triangle as shown. So we got this isosceles triangle. The two legs are 22 feet each and the base is 16 feet, right? And letter A says, why would the calculation A equals 1/2 22 times 16 not result in the correct area of the triangle? Pause the video now and see if you can answer this question. Well, there's kind of two ways that you could put this. Number one, you could say simply, the 22 feet is not the height of this triangle, right? Or you could say that the lengths of 22 are not perpendicular to the length of 16, right? Either way, the 22 feet is not the height of the triangle, right? The actual height of the triangle, right, must be perpendicular to the base. That would be the height, right? So letter B then asks us to determine the area of the patio to the nearest square foot. Pause the video now and see if you can figure that out. It's going to take a little bit of work, but I think that you can do it. All right, well, let's go through it. In order to figure out what the area of the patio is, we need to figure out the height. We need to figure out that length. And that's not too bad to do because we can always take an isosceles triangle and slice it into two congruent right triangles. Now, what we know is we know that that's 22 feet, and we know that this must be 8 feet. And what we're lacking is the height. Now, we can figure out what that height is by doing the Pythagorean theorem, right? And we can say, well, 8 squared plus h squared, that's a funny looking h, is equal to 22 squared. That's going to be 64. Plus h squared is equal to 22 squared, which is 484, I believe. Right? Of course, we can subtract the 64 from both sides. And we'll get h squared is equal to 420, and h will be the square root of 420. Now, as an aside, right, the square root of 420 is not a particularly nice number. It's kind of an ugly number. And you could certainly figure out what this thing is on your calculator right now to some decimal accuracy, whatever that decimal accuracy would be. But if we want to make sure that the calculation's nice and clean, we'll just use the square root of 420. In fact, we can say now that the area is 1/2 the base, which is 16, times the height, which is the square root of 420. And now I'm going to bring my calculator into it. Okay, 1/2 16 times the square root of 20. Uh-oh, somehow we ended up closing out our calculator here. Let's bring it back up. Let's clear this out, get out of this table that we were working in the last lesson. And let's do 0.5, 1/2, times 16 times the square root of 420. Now again, if you'd like to evaluate the square root of 420, get this messy decimal, that's fine. Just don't use the rounded version, okay? Enter, and there's my area. 163.95 square feet, I think. 163.95, what do we want? To the nearest square foot. So the area would be 164 square feet. All right, 164 square feet. Again, feet squared, yeah, whatever. All right, going back into the full screen, let's take a look at letter C. Letter C asks us, if the patio is to be covered by stone that costs $12.25 per square foot, what will be the total cost of covering the patio with stone? All right, this should be pretty easy, but pause the video for a moment and figure out what the answer is. All right, this is another example of what we call a unit cost or a density. All right, in other words, for every square foot, for every of those 164 square feet, we've got to pay $12.25. All right, so it makes sense now to simply use multiplication. In other words, I'm going to do 164 square feet and multiply by 12.25 per square feet. Right? Those square feet cancel. This is just an issue of evaluating it on your calculator, so I'm not going to kind of go there, save ourselves a little bit of time. What I found was that it was $2,009. Right? $2,009 by just working through that calculation. All right? Watch for those. Again, if you go through a problem, right, where they give you some kind of a unit cost, then you have to think about how the measurement, right, in this case the 164 square feet, will be used with that unit cost to calculate some final cost. All right, let me step out of the way, pan this up a little bit so you can look at it, and then we'll move on. Okay, let's keep going. Take a look. Problem number 5. Here we go. Back into the coordinate grid. Parallelogram ABCD has vertices at A, 0, 6, B, 9, 6, and C, 6, -2. Letter A. What are the coordinates of vertex D? What are the coordinates of vertex D? This is kind of a neat problem. See if you can figure it out by pausing the video now. All right, let's do it. Let's plot the other 3. We have A at 0, 6. We have B at 9, 6. We have C at 6, -2. And we want to figure out where D is. Okay? Well, let me connect a few of these with just nice straight lines so that we can at least see it a little bit better. There's side length AB. Kind of rotate it a little bit. Right. So where is D? Well, D is going to be somewhere over here. And we can use the fact that opposite sides of parallelograms are the same length to figure out where it is. Right? We know that wherever D is, right, it's got to be along a horizontal line from C because AB is horizontal, and it has to be the same length as AB. But AB has a length of 9 units. So if I were to just go sort of backwards from here by 9 units, I'm going to be right there, right? I'm going to be at that point. Specifically, I'm going to be at -3, -2. Let me finish filling these in. All right, let me just 3, 5, 9. Yep. Okay. And bring that back to horizontal. And have my entire parallelogram in. Great. All right. No great surprise, letter B. Determine the area of parallelogram ABCD. Show the calculation that results in your answer. All right, go ahead. Try to figure out what the area of this parallelogram is. All right, let's take a look. Well, the area of any parallelogram is given by base times height. The base is pretty simple here. And let me actually go in a different color just so that this kind of stands out a little bit for us. All right. The base length is 9 units. The question is, what's its height? Well, the height is simply the vertical distance from either A or B down to the base. And that's pretty easy because it's just going to be this calculation. And what is that? That's going to be 6, 8. It's going to be 8 units. Let me just make sure, 5, 6, 7, 8, absolutely. So now the area is going to be our base, which is 9 units, times our height, 8 units, and that's going to be 72. Again, there's no particular units in this problem because we weren't told, is this grid inches, centimeters, whatever. It's 72 square units, whatever they are. Now, one last piece of this problem, just as a little bit of review for us. Last part of this problem, letter C. Which is the longer side, AB or BC? Support your answer. All right, without using a ruler, tell me which side is longer. Take a little bit of time to figure this out. All right, well, let's take a look. One thing that we know for certain is that AB is 9 units long. Okay? Now my question is, well, what's the length of BC? And in order to figure out the length of BC, what we need to do is we need to use either the Pythagorean theorem or the distance formula, which is, I think, the way that I'm going to do it. All right? Now, what do I have? I've got B, that's at 9, 6, And I have C, which is at 6, -2. I just wanted to have those written down so we could scroll up a little bit, have you be able to see the board a little bit better. Let's figure out the length of BC by using the distance formula. Okay, let me get rid of some stray marks there. Here we go. All right, I've got 6 minus 9 quantities squared, -2 minus 6 quantities squared. That's going to be -3 squared plus -8 squared. That's going to be 9 plus 64 equals the square root of 73. Now, you probably already know, right, that the square root of 73 is going to be smaller than 9 because 9 is the square root of 81. All right, but you could, of course, always take your calculator out, type that in, and the square root of 73 is about 8.5, etc. And therefore, AB is longer. Right? Again, just a little review problem thrown in there in terms of the distance formula. And we should be kind of aware that we might have to pull from various different branches of geometry in order to solve problems that we've been doing this year. All right, so take a little look. Going up here, glance at that. All right, and now let's move on. Okay, one more problem. Let's take a look. An isosceles triangle is shown below whose legs each measure 10 inches and whose vertex angle measures 46 degrees. We want to find the area of this triangle. All right, so very blatant. I want to figure out what the area of this triangle is. I know what the legs are, 10 inches each. I know that the vertex angle is 46 degrees. All right, letter A. Find an expression involving a trigonometric ratio for the height of the triangle, leave unevaluated. All right, let's draw a picture. And by drawing a picture, I mean let's draw a line. All right, I need to figure out what this height is. Okay, see if you can come up with an expression for the height that involves a trigonometric ratio. All right, but don't worry about evaluating it. That's the whole leave unevaluated. Go ahead and pause the video now. All right, well, let's take a look. I'm going to kind of draw this right triangle, but sort of flipped like this. Now keep in mind that's 10, this is now h, and that's now a 23-degree angle because the altitude of an isosceles triangle bisects that vertex angle. Now notice the h is the side that's adjacent to that angle, and the 10 is the hypotenuse. So what we're looking at here is the cosine ratio. Specifically, the cosine of 23 degrees is equal to h divided by 10. So h is going to be 10 times the cosine of 23. Right? There it is. H is 10 times the cosine of 23 degrees. Simple. We leave it like that, unevaluated, no rounding, no messy decimals. Now that's part of what we need, right? To calculate the area of this isosceles triangle, we need the height, but we also need that base. So let's take a look at letter B. Find an expression involving a trigonometric ratio for the length of the base of this triangle. Leave unevaluated. So now we need to figure out that length, right, in terms of a trig ratio. That's a little bit trickier, but again, take a little bit of time and see if you can figure it out. All right. Well, again, what's tricky about this, going back to this triangle, my beautifully drawn right triangle, we've got that 23 degrees. This time I'm going to leave the h off. We've got that 10, and maybe I'll call this x, right? So I can easily set up a ratio, because that's the opposite side, and that's the hypotenuse. I can know that I'm going to be using sine, right? I've got opposite hypotenuse, that's the sine ratio. Specifically, I can say that the sine of 23 degrees is equal to x divided by 10. So x will be 10 times the sine of 23 degrees. Now, the problem is, that's not the base of my triangle. That's only half of it, right? That's this. That's the x, right? What I need is 2x. So the base, which is 2x, will be 2 times 10 times the sine of 23 degrees. And you could definitely leave it like that. Or if you chose, you could do the 2 times 10 and leave it as 20 times the sine of 23 degrees. Either of these would be perfectly okay. All right? So now I've got the height and I've got the base. All right? Let's take a look at C. Determine the area of the isosceles triangle to the nearest square inch. Why don't you pause the video now, use your calculator, and figure this out. All right, let's take a look. Well, the area, right, will be 1/2 base times height. We know that the base is 20 times the sine of 23 degrees. We know that the height is 10 times the sine of 23, whoops, not sine, it's the cosine. That would definitely throw my answer off. 10 times the cosine of 23 degrees. And now I most certainly need to use my calculator. Now again, if you wanted to, you could definitely do 1/2 times 20 and just make that into 10. Then you'd have 10 sine 23, 10 cosine 23, but I think we'll just put it in that way. All right? So we're going to have 1/2 times 20 sine 23 degrees, and then 10 cosine 23 degrees. Ultimately speaking, the reason that I like to put it in this way as opposed to figuring out what the height is, or actually this would have been the base, figuring out what the height is, I'd have so many messy decimals. My tendency would be to want to round them first and then put them in this calculation, but that can actually alter my final answer quite a bit. Avoid rounding intermediate answers when possible. Hit enter, and there's my area. 35.966, etc. Glass is slipping. So rounded to the nearest square something, I'll have to go back and look at that, we're going to have 36. 36 what? 36 square inches. All right, and that's the area of my isosceles triangle. This is going to be an important calculation. A few lessons ago, we did something very, very similar to this, a little bit easier, to find the perimeter of a regular pentagon. And then we use that in the next lesson to try to kind of get a grasp for the circumference of a circle. Same thing here. We've now been able to find the area of an isosceles triangle, given that we knew its side lengths and its vertex angle. Eventually, we'll be able to use this to figure out the area of a regular polygon, and then using that, we can figure out the area of a circle. All right, but take a look at this, and then we'll wrap up the lesson. All right, let's do it. So today, again, was primarily review. You should have already known that the area of a parallelogram is base times height, and the area of a triangle was 1/2 base times height. The difference in this lesson, compared to what you may have done in middle school or even earlier, was that we maybe had to use tools like the distance formula, right triangle trig, Pythagorean theorem, in order to find missing lengths, missing heights, missing bases, etc., in order to do those calculations. The calculation itself for area is quite simple. What's a little bit more tricky is using the tools of geometry that we've developed over this course in order to carry out those formulas. All right, but you'll get a lot more practice on that on the homework. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.